Here's chapter 8 on bonding and the structure of molecules. So we've already touched on these a little bit, but to get more specific, there's two types of bonds that hold atoms together. There's ionic bonds and covalent bonds. So ionic bonds are found in ionic compounds, which we already know a good bit about. We know that ionic compounds are made out of a metal and a nonmetal, specifically a cation and an anion, something positive and negative. It also could have a polyatomic ion in it, like sulfate or phosphate or ammonium. And what's holding ionic bonds together is that they have opposite charges. So the positive and the negative are keeping them together. And for this to occur, electrons have been transferred. That's why one atom became positive and one atom became negative. Okay? Covalent bonds, we've talked less about. This is where electrons are being shared between atoms rather than transferred. And this occurs in molecular compounds. And if you can remember back to molecular compounds with nomenclature, these occurred between nonmetals. So you have two nonmetals that are together from the right side of the periodic table, and there's not charges involved. Instead, there is a sharing of electrons occurring. So if we look at ionic bonding a little bit more, to talk about the strength of an ionic bond, we look at what's called lattice energy. So ionic compounds make kind of a lattice where it's just a series of positives and negatives in a web, kind of. And lattice energy is the amount of energy needed to pull apart the ions in an ionic compound, okay, to take them apart from solid into their gaseous ion forms. Okay, so if you took NaCl, which is a +1 and a -1, and you pulled them apart completely, how much energy that would require. To compare this strength or this lattice energy of two different ionic compounds, you look at two things. You look at charge first, so charge of the ions, and then if that's not different, then you look at the size of the atoms. So here, if you're looking at charges first, you would, if you were comparing the lattice energy of NaCl and CaO, you would look at their individual charges. So we have a +1 and a -1. We have a +2 and a -2. So because the CaO has higher charges, that compound would have greater lattice energy. It would be harder to pull those two atoms apart because they have stronger magnets. If the charges were the same, like for example over here, LiF is a 1 and a 1, NaCl is a 1 and a 1, then you go and look at size. Atomic radius, remember on the periodic table, the top right corner are the tiniest atoms. So lithium and fluorine are smaller than sodium and chlorine because lithium and fluorine are in period 2, whereas sodium and chloride are in period 3. So they have an extra energy level between them. So Li and F, because they have a smaller radius, they can get closer together, and therefore they pack more closely, and they have greater lattice energies. It's harder to pull two small atoms apart because their protons and their electrons are all very close to each other. The bigger atoms are easier to pry apart because there's more distance between the protons and the outermost electrons. Here for covalent bonding, this is where we really are going to spend the rest of the chapter pretty much. Covalent bonding are when electrons are shared. Remember, they're being shared between nonmetals, so we're talking about the atoms on the right side of the periodic table. And we do have two types of covalent bonds that can occur. There's polar covalent bonds and nonpolar, and they depend on this characteristic called electronegativity. Electronegativity is the attraction of an atom for its shared electrons. So if you have two atoms that are sharing electrons, it's how strongly each atom's nucleus is pulling on those electrons. There's a trend on the periodic table. You can exclude the noble gases because we're not going to see them in compounds very often. We will, but not a whole lot. Noble gases are stable on their own, so they don't make bonds very often. So if you forget about group 8 and you start at group 7 with the halogens, up at the top right, fluorine is going to be the most electronegative atom on the periodic table. So he pulls on shared electrons stronger than any other atom. And so as you move away from him or down from him, you become less electronegative. That's the trend. So for a nonpolar covalent bond, if you have a nonpolar bond, that means that the electrons are shared very evenly. There's an even distribution of charge So there's not a side that's more positive or more negative. And this occurs when there's two atoms of identical electronegativity, because if you think of two hydrogens, they're identical atoms, right? So they're both pulling with the same force on their shared electrons. Therefore, the electrons are smack in the middle of the molecule. Same with O2. You've got two oxygens pulling on the electrons with even forces, and so the electrons are going to reside right in the middle. So all of these atoms are identical and therefore are nonpolar. Whereas if you are a polar covalent bond, you have two atoms that have different electronegativities. So for example, H and Cl. If you think about the atom that is closest to fluorine, because remember fluorine is the most electronegative, chlorine is much closer to fluorine than hydrogen. So chlorine has a greater electronegativity and pulls on the electrons more strongly. Hydrogen is very wimpy and pulls on the electrons with very little strength. So if you can imagine the electrons being shared, they're going to be shared, but they're going to be closer to chlorine than hydrogen. Similarly with HF, it's two different atoms, so fluorine is pulling on the electrons more strongly, and the electrons are going to reside closer to fluorine. So that's called a polar bond. And one side becomes partially negative and one side is partially positive, is what we say. So the one who is more electronegative will be the negative side of the molecule, and the side that is pulling with less strength will be the positive side. If you look at C and O, try to think which side will be more negative and which side will be more positive. The O is closer to fluorine, so he pulls with a greater strength. The electrons are going to reside closer to him. So his side is going to be partially negative. Carbon's going to be partially positive. Same with N and O. And here, one thing I try to use as an analogy is two kids that are pulling on a toy. If it's two evenly matched kids, the toy will be right in the middle as they're both pulling on it. Whereas if you put like a 10-year-old and a 2-year-old, the 10-year-old is going to pull the toy closer to them than it will be to the 2-year-old, as an example of a polar bond. So the way we kind of measure polarity, first off, we can just say, is a molecule polar or nonpolar? But then we also can talk about the degree to which it is polar. So the bigger the difference in the electronegativity, the more polar it is. Like if you think about the two kids with a toy again, if it's a 2 and a 3-year-old, it might be a fairly even match, but the 3-year-old just might pull the toy a little bit closer to himself. That would still be polar because one person is pulling harder. But if you put a 2 and a 10-year-old together, that would be much more polar because the 10-year-old would pull the toy much closer to himself than the 2-year-old. So similarly, we can talk about this thing called a dipole moment, which is just a number. The dipole gives you kind of a degree of polarity. We won't do any calculation with this, but what I want you to see here is the bigger the electronegativity difference, the bigger the polarity. So like you can look up a number value for electronegativity for every atom. So like H has a value and F has a value. And what this chart tells me is that they differ by 1.9, and their dipole moment, which means how polar they are, is 1.82. Whereas if you go down here to H and I, remember I is way down the periodic table from fluorine. So I is not very electronegative. Hydrogen, not very electronegative. They're both very wimpy. They only differ by 0.4. Do you see how they differ much less than the H and the F? They differ less and they have a smaller dipole because they don't have as much of a polarity or a difference between their electronegatives. So what we would say here is the greater the difference in electronegativities, the greater the polarity. One kind of quick test for this though, because we don't normally have the values, is to look on the periodic table. And if two atoms are far away from each other, then most likely it's going to be more polar. If they're really close to each other, like C and O or N and O, those two, N and O specifically, they're right next to each other. That's not going to be quite as polar as, say, H and F.